Hi everybody, this is MG5004 and the DE equivalent. This is topic 2. Now this is class 2, but I'm going to have to divide it into probably 3 parts. So this will be part 1. You'll see the slides for the rest of the presentation, but they'll be blank. So this, I'm going for the first 10 slides. After that, you'll see the rest. So this is topic 2, class 2, part 1. At the end of topic 2, class 1, we got as far as looking at f of g of x and g of f of x, and we looked at how actually which one you do first makes a difference. You do the bit in the bracket first. If you do g of x first and then you perform f on that, you get a different result from if you perform f of x first and then g on that. But there's something else we can do. We can actually perform f and then the reverse process, and as you would imagine, we then end up with where we start with. So we put our input in, we put in x, something happens, the process happens, out pops the result, and if we pop that result into the next machine, if you like, which does the reverse process, and we use the notation f to the power of -1, it's not to the power of -1, it's actually just notation, and out pops x. And if that happens, what we're talking about is we're talking about the inverse function. Now, in order for for an inverse to exist, it actually only exists if the result, what you get when you're looking for the inverse, is itself a function. So for a function to have an inverse, the result, which I'll show you how to find in a minute, must be a function. So you've got this idea that if you start with a function and you do something and then you end up with a function itself, then it's the inverse. And what we're actually doing is we are taking the mirror image of the function. So we take the mirror image, and if that mirror image is a function itself, then we have found the inverse. Let's have a look at an example. We can do these algebraically like this. So suppose we've got as an example that y, or f of x, is equal to a fifth brackets 4x minus 3. Now the first step is to rearrange, and we rearrange so that x is now the subject. So let's do that. Let's multiply both sides by 5. So we get 5y. Let's add on 3. And let's divide by 4. That gives us x. Now the second step is to interchange the x and the y. This is the mirror image bit. So now we get that 5x plus 3 divided by 4 is equal to y. And this is now the inverse function. So this is now the inverse function like that. And if it is, what we found will be a function. Now, it is a function. We can see easily that that's a function. It's got a unique output. But also, we can do a check. Suppose we put in 2. Now, if we put in 2 into the original function, so it would be a fifth times 4 times 2 minus 3, which is 1. Now, if we're correct, if we now put 1 into the inverse, we'll get back to 2. So we're going to put it into a quarter of 5 times 1 plus 3, and if we do that, we get 2. So yes, so on both counts we've found that it is the inverse. The left-hand function is the Fahrenheit to centigrade conversion. So it's 9/5x plus 32. Now obviously its inverse function is going to go the other way. But if you have a look at f of x is the blue function. And if we reflect it in the line y equals x, which is the dotted line, we get the other function. So that is its inverse. So y equals g of x there is the inverse. It's reflected in the line y equals x. Similarly, if we look at the second function, if we look at b, the function here, which is the blue lines, is equal to x plus 2 over x plus 1. Now, again, if we reflect those in the line y equals x, the 45-degree angle line, we'll now get the black pieces. So this one reflects to give us this one, and this one reflects to give us this one. So we're reflecting each part this time in the line y equals x. Each time it's going to give us the inverse. Each of those bits are functions, so that's fine, and we could work out what the inverses were by rearranging it algebraically as we did on the previous slide. Have a look at diagrams A and B, and we see from A and B that there's no immediate inverse function corresponding to y equals f of x equals x squared, because when we do the algebra we get y squared equals x, which is not a function. It doesn't meet the vertical line test because for each x is going to be 2 y values. So it's not a function. But what we can do is if we say, well, if y is only equal to this top half, then it's only going to be equal to the positive square root, then yes, indeed, we can find the inverse. So if we limit our domain in the first instance, then we can find the inverse. So sometimes, yes, you can find a limited inverse by limiting the domain to get this sort of situation. Sometimes, though, you're asked to deal with a parametric representation of a function, where you have a function, the normal x and y, but they're represented by some third variable. In this case, it's t. So the representation is that x is equal to t cubed, and y is equal to t squared, where t is an element of the real numbers. Now you could do this by setting up a table. Like that, and you could just choose some values of t, maybe up to 4, and then you could find x. So x is t cubed, so it would be negative 64, and y is t squared, so it would be 16, and so on. And then you can plot x and y as normal. That's one way of doing it. Or you could use Desmos, which I've mentioned before. You could do Desmos graphing calculator, in which case then you just type in t cubed comma t squared, and this recognizes that that is the x coordinate and that is the y coordinate, and it will give you the graph. You will need to specify some sort of domain, so you might want to say that negative 4 is less than or equal to t, which is less than or equal to 4, or whatever numbers you want to choose. So you just have to specify the domain a little bit. Either way, you get what we call a semi-cubical parabola, which has a 0 point at 0, which you can see from the table of values. For later in calculus, we need to be able to describe the nature of various functions, and quite a lot of the next slides are doing that. I just need to make that a little smaller. Particularly, we need to look at the continuity of functions. Have a look at A at the top left. That is continuous. You can draw that without lifting your pen. But if you look at B, it's got a gap in it. We couldn't just draw it without lifting our pen. We'd have to lift our pen. So we say that that is discontinuous, or discontinuous function. In the third graph on the slide, we've got a very odd sort of function, and we've got a break in it at 0. So let's have a look at what happens as 0 approaches. Let's come in from the left. So let's look at, and this is how we write it, x is approaching 0 from the left. So we say there that the limit of f of x is 3 as we're coming in from the left. But as we come in from the right, we write it like this, then the limit is actually 0. So we're coming in from the right hand side and the limit is 0. So the limits aren't equal. So then it's indicative of a discontinuity there. Maybe we could look at another point. Let's have a look at x equals 3. So again, let's come in from below. What's that as you need to say? That's tending towards. So coming in from below, then the limit is 9. If we take that, and the function's x squared on this part, then the answer is 9. So if that's y equals x squared on this side. And if we come in the other way, as x tends towards 0 from above, so we're coming in from above, again, the limit is going to be 9. So where the limits are equal, then the function is continuous. So at x equals 3, the function is continuous. The next part, topic 2, class 2, part 2, will start at slide 9 next time.